how would you describe this method's implementation? Someone asks you to explain how that method works, not the comment, but the actual code. What would you say? How's the method work? What's the method do? Yeah?
It performs a function on the given string and then evaluates it to its original function, or to the original string.
Okay, so it performs a function on the string and then evaluates it. That's a little too high level and vague. Specifically, what does it do? Yeah?
Checks to see if it's spelling forward if it's the same as it is backwards.
Okay, so it's checking to see if it's the same forward and backwards, but again, specifically, yeah?
We'll create another string that's the reverse and then compare the original to the reversed one you just created.
Okay, so yeah, so it reverses the string, obtain a new string, compares it to the original, and that's how it decides if it's the same backwards and forwards. So you might say it returns whether or not S and its reverse are equal. It's another way to put it. So, you know, you got to sort of get the right level, but people don't have trouble doing that. Okay, this is what you would not say. If I say, what does this method do? And you said, well, it creates an empty string R, it iterates through S from left to right. As it encounters each character C, it appends it to the beginning of R. Next, it iterates through S and R, comparing corresponding characters. If any are found that are not equal, returns false, otherwise returns true. Why is that not the way anyone would describe what this does? Why is this too much detail? Yeah?
You don't actually understand like what it's for.
Well, it certainly obscures the larger point that's obvious here. But, yeah.
You're describing it character by character instead of just by the string.
Okay, I'm doing it character by character instead of by string. Yeah.
It's inflexible since you're only describing one specific algorithm when it could possibly be optimized.
Okay, I'm describing one possible way that reverse and equals might work. Yeah.
You're purposely describing the reverse function and not the is palindrome function.
Okay, that's getting at what I had in mind. He said you're purposely describing the reverse function instead of the is palindrome function. My point is, you've got to use abstraction when you talk about programs. If you're going to describe what this code does, you describe what the code does. You don't describe what reverse does. You just assume reverse does what it says it does. And you assume that equals works. So you say it reverses the string and then compares the string and its reverse for equality. You don't start describing what happens inside these methods, because where would it end? We'd have to come down and say, well, what's an empty string? Or how do you iterate? What type of loop is used? How are characters represented? You know, we have to work at a certain level of abstraction or we just make no progress. And that's just something you internalize as you learn the program. Okay? So here's a sorting algorithm. How would you describe how it works? Suppose you're teaching a discussion section at 2420 and you're trying to explain how merge sort works, which is what this is. What would you say? Yeah?
It divides the list in half and then sorts each side.
Okay? It splits the list. Well, actually it doesn't do any dividing, but I mean it doesn't physically divide. Yeah?
So would a good answer be what the comment says?
Well, right, that's the high level. I'm asking you to explain the implementation, how the implementation works. Yeah?
It sorts the two different halves of the array and then like put them back together.
Okay, sorts the two halves of the array, puts them back together. Yeah?
Would it be viable just to say it uses merge sort on the array?
Well, this is merge sort, so we're trying to explain how merge sort works, basically. Yeah?
It's breaking it into individual pieces, sorting them, putting them back together. And
Okay. Maybe sorts the top half of the array, sorts the bottom half of the array, and merges the two together to produce the result. Yeah?
So keep having the array until you can't have it anymore, and then put the arrays back together in order as you go back up.
Okay, he said split the arrays in half until you can't split them anymore, and then put them up together as a return from the recursion, something like that. Which is what I'm glad you said, because that way of describing it, that you split things in half until you hit the bottom of the recursion, and then you work your way out, is the way a lot of people describe recursion. But describing it that way is like describing this thing this way. It's too much detail. You're getting in, just like you don't peer into reverse and say how reverse is implemented. You don't peer into sort and explain how sort works here. Right? You just say, sorts the top half of the array into ascending order, sorts the bottom half of the array into ascending order. You don't say that it sorts the top half into ascending order by splitting the array in half and sorting the top half of that into ascending order and, something like that. You don't drill down to explain how sort works. You just assume that sort, and merge all work according to their specification. Sort the high half, sort the low half, merge the two halves into an array. Okay? So, there's my description. If A has fewer than two elements, does nothing, otherwise sorts the first half of A, sorts the second half of A, and then merges the two halves. And what you don't say is, splits A into half and keeps doing that over and over until the array has fewer than two elements. Then merge on the way up. Give the recursive method calls the same respect you give the non-recursive method calls. None of you tried to describe how merge worked. You just said it merges. Don't try to explain how sort works. It's just a method call that does what it says it does. Yeah?
I don't believe that function would not do anything if it had fewer than two elements, because high-low is greater than or equals to 1. So even if there was one element, it would still perform the sort, or attempt to sort.
No, if there's two elements, the high and low are the same. If there's one element, high and low are the same. If low is a low index and high is a high index, and there's only one, the low and high index will both be 0. One element array has one element. The high element of the index is the same as the low element index. Anyway, that's not a major point. Okay? So we're going to be doing a lot of recursion coming up. And I just want to prime you to think about recursion the right way. When you think about recursion, you don't think about it calls, it calls, it calls, it calls. You just think it sorts, it sorts. It's immaterial that it's a recursive sort. Yeah?
Assuming sort is an explanatory name, would you at least say that it calls itself?
There's really, well, when a method is recursive, there's one extra thing you have to argue that it's correct. You have to argue that it terminates. And for that, you have to admit that it's calling itself, yes. All right, now, I'm going to talk about something else you're familiar with, addition. So, here we're doing addition of 2 3-digit numbers. And I want you to think, this is an algorithm that everyone learns in school. And I want you to think of it in terms of what the operations are. So the first step is to add the 9 and the 6 and a 0. Now why do I have a 0 here? Where does the 0 come from? Right, there's a carry. There's a carry in from a previous operation, and initially it's just 0. So we add 0, 9, and 6, and we get 15. Now how do we decide to write a 5 there and to carry a 1? How do we compute the 5 from the 15? Yeah?
It's 5 more than 10, which is the base.
5 more than 10, sure. What's another way? Yeah?
The sum, the 15 mod 10.
Yeah, it's just the mod. So we're working in base 10. So we just take the sum and take it mod 10, and we get 5. So you take the sum, mod the base, and that's what you write there. You take the sum and divide it by the base, and that's what you carry. So you can describe this in terms of mod and division. And because you're working in base 10, it's simple to take mod 10 of this. You just take the last digit, and to take div 10, you take the first digit. But essentially, you're doing a mod and a div. All right, then you've got 1, 4, and 2 to add, and that's 7. So the digit you write is 7 mod 10, which is 7, and the carry is 7 divided by 10, which is 0. But once you understand that, it's really easy to work in a different base. So we can take these two numbers and add them in base 8. Again, we add 5 and 6, we get 11. Mod 8 is 3, divide by 8 is 1, and that determines the 3 and the carry. And 1 plus 2, 1, 2, 3 is 6, and again, we do the mod of the div. So as long as you know how to add 3 digits, 3 numbers I should say, 3 numbers, you can add in any base just by knowing how to do mods and divs. Now, let me ask you this question. Suppose you needed to have arbitrarily long integers. So you wanted to have arbitrarily long integers, like there's a big int package in Java. In Python, integers are automatically long integers. And you need to be able to add them, multiply them, and so forth. How would you represent them? So you have a big integer class. How would you represent a big integer object? What would be the instance variables? Yeah?
Text,
Okay, what kind of text? Like,
ASCII.
okay, so like we'd represent 1,523 by the string 1523. Okay, that's one idea. String of digits in Unicode. Yeah?
A linked list of primitives,
What's a primitive?
like a C and or a C long, and then a pointer to the.
Okay, so he's saying a linked list of ints, basically. Any other ideas? Yeah?
Yeah, just an arbitrary amount of integers, and we represent each one as a new, as essentially essentially as a new digit in a base system of that, not the max integer size.
Okay. How would you glue all the digits together, I guess is the...
You just have functions for the operations, and when you when you exceed over 1, you just mod. You can just mod the.
Okay.
But
But we need some kind of, no matter what base we're working, we need some kind of list or something.
An array list?
You could have an array list of digits. So I've listed some out here, a string of digits, an array of digits. So in both of these, we're actually representing each digit as a Unicode character. An array of integers, an array of integers in base 2, an array of integers in base 16. So let's discuss. What's attractive about just using a string of digits? Yeah?
You don't have to worry about overflow.
Well, you don't have, you said, okay, but you don't have to worry about overflow here either. What's it, oh, why do you prefer a string of digits over a string of ints? Yeah?
It looks the most familiar.
It certainly looks familiar. Yeah?
You can print it.
It makes it easy to print. Right? So the operation that takes the int, the long int, and converts it to a string is really easy to implement because it's already a string. But what's the downside?
Performing arithmetic sucks.
Right. Every other operation. He said performing arithmetic sucks. Every other operation is hard. Because the Unicode value for the character 5 is not 5. I forget what it is, but it's not 5.
53.
53. And the Unicode character for 6 is 56. So when it comes time to add, multiply, divide, or whatever, you've got to convert from characters into something you can actually do arithmetic with. So unless you plan to do almost nothing with your long integers except read them in and write them out in base 10, that's not going to work out so well. Those first two don't work. Now, what about here? An array of integers in base 10. Like I say, we'll go with an array of integers. But how could we decide what base to use? I mean, what would the algorithm look like for adding two integers represented this way? So you have two arrays of ints. What's our algorithm for adding them? Yeah?
You start at the last position and you add them together and then you carry them.
Yeah. You just line them up. You start with the last position. You have a carry in of 0. You add the 3 digits. You get a number. You take it, mod the base, you take it div the base like we just saw, and you produce a new array as a result. And you can work in any base. It's just if you're working in this base, again, this is an array of ints with ones and zeros. You would add them and take everything mod and div 2 or mod and div 16. Okay? Is there any advantage to using one base over another? Yeah?
If we use a base that's the size of the maximum integer, since our integer, we're using the most efficient.
Okay. So he's saying that the bigger the base, the more efficient.
Well, if we use one that's the same size as our primitive data.
Well, even if we don't go to the same size, why is it going to be more efficient to use base 16 than base 10? The arrays are shorter. The larger the base, the fewer the digits. Now, is it any more expensive to add 2 ints between 0 and 9 than to add, is that less expensive than adding bits that can range, ints that can range between 0 and 15? No. Their int is built into the hardware. And as long as your numbers you're adding aren't bigger than the largest int allowed by the hardware, it takes the same amount of time to add tiny ints and giant ints, large ints. 32-bit ints take the same amount of time to add as 1-bit ints. So it would be silly to use this representation because you're wasting most of the bits in the number. They're all zeros except for the last bit, possibly. So the bigger the base, the better. Now, what if you had to choose between base 16 and base 17? Yeah.
I would use 16 just because of convenience. There's a lot of documentation on hex and other things on hex, and people are familiar with hex.
Okay, he's arguing base 16 for familiarity, so let me change it. What if you had to choose between base 32 and base 33? Yeah?
32.
Okay, he said 32 because it's a multiple of 4, but what's that got to do with?
Better for the hardware.
Better for the hardware? Yeah?
The CPU does everything in base 2, so it's easier. It's cleaner to go from base 2 to base 16 than it is to base like 17.
Okay, well, there is a much more concrete reason, yeah?
Because it needs an extra bit to store the number if you're in base 32.
Well, he says it uses an extra bit for base 33, but you're just wasting those bits. I mean, it makes the representation slightly shorter. So the argument's always in favor of the larger base, except
We can use the bit shift operation in the mod in place
Right.
of the mod operator.
if you use a base that's a power of 2, div and mod just become bit shift and bit masking operations. If you want to divide a number by 32 and throw away the remainder, all you do is throw away the low 5-order bits. You do a bit shift. And that's a fast operation on a computer, a lot faster than division. And if you want to do a mod by 32, you just throw away all but the low 5 bits. And that's a bit mask. Again, fast. So what we want is a base that's big and a power of 2 and not so big that we get an overflow when we multiply 2 of them. Because we don't want to use base 1,000,000 because the computer can't deal with base 1,000,000,000. We want to pick a base that's a power of 2, as large as possible, and can be done in a single instruction on a computer without overflow. So what base would that be? Let's say you have a 64-bit computer, as they are today. So you can get up to 64 bits worth of integer. What base would we use? We'd use 32, because when you multiply two 32-bit numbers, you don't get more than 64 bits out. If we used a higher base, we're going to get overflow when we multiply digits. So our base is going to be base 2 to the 32 power. And we're just going to have an array of ints. So this is all stuff that I've said. The bigger, I still won't dwell on it because I already said it. We're going to use a really big base, 2 to the 32. So each digit will just be a pattern of 32 bits. That way we can do arithmetic using 64-bit math, which we have. The largest product is what we really care about. So that's the largest 32-bit number times the largest 32-bit number. Anyway, it's less than 2 to the 64. This is the largest thing we can get. This two largest numbers being multiplied and the largest possible carry is still less than 2 to the 64. And it's fast to do the div and the mod. We're just bit masking or bit shifting by 32 bits. Now, if you looked at, suppose you had an array of 32-bit ints, and you just looked at the bits in those 32, what would you see in that array? Just looked at the array from left to right, what would you see? What if you looked at one 32-bit integer, and you looked at the ones and zeros? What do you see? Yeah?
Don't you just see what the bits are?
Yeah, you see a base 2 number, basically. And so if you had a bunch of them in an array, you see a really long base 2 number. So what we've gotten to here is, you just take the base 2 representation, chop it up into chunks of 32 bits, store each of those in an element of the array, and that's your representation. So it shouldn't be mysterious. But the way to think about each int in the array is as a number in a gigantic base. Okay, so if I give you 2 n-bit integers and ask you to add them with grade school algorithm, what you learned in school, what's the complexity of adding 2 n-bit integers? Yeah, it's O of n. We already saw. Now these aren't n-bit integers; these are n-digit integers, but it's the same order of complexity. The difference in the number of bits it takes to represent a number is about 3 times the number of digits it takes to represent a number. So if you have 2 n-bit integers or 2 n-digit integers, it takes n operations to add them together, n steps. Now, what if you have 2 numbers? Suppose you have 2 numbers, a number x. So x is the value of a number, and you've got to add it to itself. What's the complexity of that? What's the complexity of adding x to itself? How many steps will there be? Well, x can be gigantic. X can be trillions or quadrillions. Yes?
Just however big x is.
It depends on the number of bits in x, right? How many bits are in x? No, I didn't say, I don't know where n came from. I didn't say n. You've got to get the answer from x. It's log x. So adding, if I tell you the magnitude of a number, if I say this number, magnitude is x, the complexity of adding it to itself is log of x. If I tell you the number of bits is n, then the complexity is O of n. So you've got to be careful whether we're talking about the length of a number or the magnitude of a number when we talk about complexity. So the number of bits it takes to represent a number of a given magnitude is log of that magnitude. What about the complexity of multiplying 2 n-bit integers? Using the grade schools. Set n squared. So let's think about that. Where do the n squared operations come from? Here we're talking about 2 3-digit numbers. Yeah?
You essentially have to iterate through the top number, the number of times there are now digits in the bottom number.
Right. You take this and you multiply, multiply, multiply. Then you do this and it's multiply, multiply, multiply. So there are 9 individual multiplications that you're doing. Plus you're doing some additions later, but it's the n squared multiplications that drive the complexity. So that's n squared. Again, where n is a number of bits. What will be the complexity of taking a number x, a number whose magnitude is x, and squaring it using this grade school algorithm?
Log x squared.
Log x squared, the square of log x. So log x would be the number of bits, or the number of digits. It all differs by a constant. And it's proportional to the square of the number of bits. Let's invent a new algorithm. Maybe we can do better than grade school multiplication. Why should that be the best of all possible algorithms for multiplying? So let x and y be n-bit integers. We're going to split x and y into halves. So I'm going to call the left half x sub l and y sub l, and the right halves x sub r and y sub r. And you'll have to agree that x is equal to is that right?
I guess we'll find out.
Yeah, that's right. Okay, so we can do x and y like that. We can recompose. We can reobtain x from xl and yl by basically shifting xl to the left by n over 2 bits, and then sticking xr where we just did the shift. So x is 2 to the n over 2 times x to the l plus xr. Y is 2 to the n over 2 yl x for yr. If we multiply, we're just doing this. We're trying to derive a recursive multiplication algorithm. So I've rewritten x as this, and I've rewritten y as that. And if you want to think about base 10, like, what's 52? If we're using base 10, 52 would be 5 times 10 plus 2, right? So it's 2 digits, we divide the 2 by 1, divide the 2 into halves, so that's why we get 10 to the first, if we're working in base 10. Okay, we can expand that out. And we get 2 to the n times this, plus 2 to the n over 2 times this, plus that. So I just did a little algebra there. And what algorithm does it suggest now? Where's our recursive multiplication algorithm? It's staring right at you. You want to multiply 2 large numbers. How do you do it? Yeah?
Oh, I thought you were after the complexity.
No, not after the complexity. I just want to say, what's the algorithm? Yeah?
Can you do the same multiplication for like XL and YL and
Right.
XL?
We've reduced the problem of multiplying x and y, which are n bits long, to the problem of doing these 4 multiplications. But how long are the numbers? They're just half as long, n over 2. So by splitting the numbers in half, we've taken the problem of doing 1 long multiplication to the problem of doing 4 shorter multiplications. And of course, we can turn around and take the 4 shorter multiplications, and each of them we can apply the same trick until we get down to some number we're willing to multiply normally. So imagine you had an array of length 1,000 of integers representing a big N. This is saying, okay, one way you can multiply them is by splitting the array in half, doing 4 multiplications of the halves, and then you could recombine it using this formula. Yeah?
Can you just explain the way that you're splitting x and y?
All right, let's look at an example here. Okay, so let x be 23 and y be 51, but instead of using base 2, I'm going to use base 10. And instead of n being the number of bits, it's going to be the number of digits. So what's n in this case? 2. So I'm going to split 23 into, the left half is 2 and the right half is 3. And for y, the left half is 5, the right half is 1. And you'll see that our original x is going to be 2 times 10 to the 1 plus 3, right? 2 times 10 to the n over 2. N is 2 in this case. So 2 times 10 plus 3. And y is 5 times 10 plus 1. Okay? So then plugging back up into this formula here, we see that 23 times 51 is 2 times 5 times 100 plus this product times 10 plus that product. I'm not doing anything mysterious here. I'm just using place values of the digits. And if you work that out, you just have to trust me, that's 23 times 51. And we did it by, in the end, we only had to multiply single digits. You didn't have to do 2-digit multiplication. Okay, so do you believe that works? Yeah, I believe it works. And before I go there, how would you describe the algorithm? If you had to teach it to grade school kids, how would you describe it? What do you do? Yeah?
Split your number, X or Y. You count how many places you have for X, and that will become your exponent of the base.
Sure.
And then you have to use that base with that exponent to multiply your left-hand side of X, and then you're gonna add.
Well, no, you don't ever do this here. Let's skip down to here. So you split the numbers in half. You do 4 specific multiplications with the half. And now you've got, and plus this addition. And now you've got this answer, and that answer. And then to recombine them, you have to do some digit shifting if you're doing base 10, or bit shifting if you're doing base 2, and then add things together. But it's, you take one multiplication, turn it into 4, and then recombine in a certain way. So, there's our algorithm. And if we count it, if we're trying to do the complexity, you'll see that we have to do 2 splits of numbers. We have to do 4 recursive multiplications of numbers half as big as the original. We have to do an addition of n-bit integers and a multiplication, which actually is just going to be a bit shift. This multiplication is also a bit shift. And a couple of additions. And the question is, how do we figure out the complexity of recursive multiplication from this accounting? And what makes it hard? What makes this different from analyzing selections or insertions? Why can't we just add all these up and have our answer? Yeah?
One of them is recursive, so you have
Right.
to analyze the effect of that one.
So to get the complexity of this whole algorithm, we have to be able to figure out the complexity of that sub thing. But the complexity of this is what we're trying to figure out here. Right? So here's how we're going to do it. So there again is my accounting. And I can do all of them except for B up here, the 4 recursive multiplication. But, splitting in half and making basically two copies, that takes linear time. The addition, all the additions take linear time. And the bit shifting, multiplying by the power of 2 is just bit shifting. That takes linear time. So it's all linear, except for that unknown step right there. So here's the trick. Let t of n be the time required to multiply 2 n-bit integers. Now what we're saying then is that the time to multiply 2-bit integers is equal to whatever time is taken for step B, plus all the other time. Well, what is all the other time? O of n. And if t of n is the time required to multiply 2-bit integers, what's t of n over 2?
Half the time.
It's the time required to multiply 2n over 2-bit integers, and we do that 4 times. So essentially, t of n is equal to 4 times t of n over 2 plus some O of n term. And if we could solve this thing here, then we could figure out the running time of this algorithm. And then to finish the job, the time it takes to deal with the 1-bit integer is just constant time. That would be our base case. Base case, we're not going to do any splitting. We'll just, we've got 2 1-bit integers to multiply, we'll just multiply them. So this is called a recurrence relation. And there's our recurrence relation. T of n is equal to 4t n over 2 plus O of n. So, n is the size of the problem. Where did the 4 come from? Yeah?
The amount of times you had to perform recursion.
Say again?
The amount of times you had to perform recursion.
Right, the number of recursive calls we made to multiply 2 n-bit integers. We made 4 recursive calls. Where does the n over 2 come from? Yeah?
Dividing each in half.
That's the size of the problem when you make the recursive calls. Each of the 4 recursive calls, the size of the number is half as many bits as original. And then the O of n is a bound on the non-recursive parts of the multiplication. And then typically this is always going to be the same. It's going to say that the time it takes to deal with one bit or something of size 1, something of constant size, is constant time. So just as we did lots of summations to deal with iterative algorithms, to deal with the recursive divide and conquer algorithm, we're using our right of recurrence relation. And we don't even have to solve that recurrence. All we have to do is put a big O bound on it. So if we could say that is, suppose we could argue that T of n is O of n, what would that mean? If we could say that if we could prove that T of n is O of n, what would that tell us?
That complexity is over.
That would tell us that since T of n is the running time of recursive multiplication, if we could prove that that function right there is O of n, it's recursively defined, but if we could say it's O of n, then we could say that the recursive multiplication algorithm is linear time. Yeah?
Would we add a worse O of n if that's something we had in our instructions? Like instead of O of n, we would have had O of log of n. Would that have been what we add to it?
Sure.
The weakest link?
What we do is, so where that O of n came from, is we just figured out the complexity of all the non-recursive steps.
Right. So if one of those would have been something that's not O of n, and the
Well,
rest are still...
yeah, if one of them had been O of 1, overall would still been O of n.
Right.
But if one of them had been O of n log n or O of n squared,
You go to the worst.
we go to the worst, yeah. Yeah, we're just doing regular old algorithm analysis on the non-recursive parts of the algorithm. How much time does it take to do the setup for the recursion and the cleanup after the recursion? And then how many recursions do we make and how big are the inputs to those recursions? So when we analyze recurrence relations, when we analyze divide and conquer algorithms, such as recursive multiplication or merge sort, we're going to use recurrence relations. But what remains to be seen is how do we take a recurrence relation like that and put a big O bound on it. I'll give you a hint. You can't put a big, the bound on T of n is not O of n. We haven't found a linear time multiplication algorithm. Yeah?
So don't you have to factor in the actual division itself in each function call as well? Like, so each iterative part of T of n involves a split, and then it goes into the next iteration of that function T, right?
Well, think about what you do to multiply two n-bit numbers. This is the complete list. You split two numbers, you do a couple of additions and some bit shifting. Those all take linear time. Plus, whatever it costs to deal with those 4 recursive calls. Now, hidden in that is a whole bunch of other stuff. That's where those numbers will be split, and they'll make recursive calls, and those numbers will be split. But that's just the cost of multiplying 2n over 2-bit integers. So the recurrence relation expresses the cost of dealing with a problem in terms of the cost of dealing with smaller problems. So the unknown here is T of n. So essentially we've got to solve for T of n, or in our case we're just going to put a bound on T of n. Yeah?
Is it even possible with the recursion? Like, would it be just more accurate to give the state like we did for T over n, T of n over 2, just give its bounds or its own value instead of trying to give it no bound?
I'm not following what you're saying.
Sorry.
Maybe you talk to me later about that.
Yeah.
Right? So our goal is going to be figure out how to cope with these, with recurrence relations, how to put big O bounds on them so that we can analyze divide and conquer algorithms, which is what we're going to be talking about. And also, just to answer our question, what's the complexity of recursive multiplication? Is it better than n squared? That'd be nice. So let's take a quick break and we will finish.
Pause the recording. It's going.
Okay, so we're going to sneak up on this problem of dealing with recurrence relations by considering some divide and conquer algorithms. So divide and conquer algorithms are one, like merge sort or recursive multiplication, where you take your original problem and solve it by breaking the problem up into sub-pieces, solving the pieces, and then somehow recombining the pieces to get your overall answer. So you can view binary search as a divide and conquer algorithm, because we split. We're doing a binary search of an array, and how many sub-problems do we produce? If you want to view it as divide and conquer, we divide the problem of finding an element in an array like this by doing what? Yeah, you cut it in half. So by doing a probe, you throw away one half or the other. So your recursive call is on an array half as big, but there's only one of them. So that's a form of divide and conquer. Now, just in order to meet my pedagogical needs, I'm going to analyze a brain-dead version of binary search, which just, when it splits the array in half, it actually copies the array. So once it figures out which half to examine, it's actually going to make a copy for no good reason, other than it just makes my example work out better. So here's the algorithm. If the length is 0, return false, we didn't find it. Otherwise, we get the midpoint. If the midpoint contains x, we return true. So that's sort of a best case. The worst case is we didn't find it. So what we do is we figure out which half it's in, we copy that half, and then search recursively in the copy. That's familiar to everybody. Binary search, and there's the recurrence relation for it. So where do all those numbers, I highlighted things with colors, where did that sort of bluish 1 come from? We're saying the time it takes to do a binary search on an array of length n is, yeah?
Sorry. You're only searching one of the halves.
Okay, we're making one recursive call. So time it takes to deal with something of size n is the time it takes to deal with one thing of size n over 2. Plus, where's the yellow O of n come from? Yeah.
The time it takes to search for I can't.
Yeah.
Everything else,
Yeah. That's always the answer. It's the time it takes to do everything else except for the recursion. So we're just looking at this and we say, okay, the time for this plus this probe here, plus this probe, this comparison here, this copy. The time it takes to do all the stuff exclusive of the cost of the recursive call. The cost of the recursive call is right here. The cost of everything else is right here. So why O of n? Why not O of something else? Yeah?
Because the heaviest cost is when you have to iterate through the entire list.
Well, we're iterating through the entire list. Yeah? It's the copy. Making the copy of an n over 2 element array is O of n. Now, what if we didn't have a copy? What if we just used the original array? There's no reason we can't. Yeah? It'd be constant. It'd be O of 1. So real binary search, it's constant setup time to make the recursive call, and you make one recursive call. So for real binary search, it would be t of n over 2 plus O of 1. Okay? Now, I could make it O of n squared if instead we had it, before it made the recursive call, it just did a selection sort on the original array, just for no good reason. That would make the everything else be more expensive. So let's make a picture and try to figure out the actual complexity of binary search, of copying binary search from it. So what I've got is, at level 0, when the method is first called, it gets an array of size n. So at the next level of recursion, how many arrays have to be searched and how big are they?
N over 2.
Right, one of size n over 2. What about at the next level? One of size n over 4. What about the kth level?
2 to the k.
Well, I guess I don't have a picture for it. But it keeps being divided by, it'd be n over 2 to the k. So let's talk about the amount of work required at each level now. How much work is required at that top level? Right, at that level, the major part of the work is the time you spend copying half of the array, plus some low-level stuff. So it's roughly n over 2. The amount of work done is proportional to n over 2. How much work is done at the next level of recursion? N over 4, again, that's the copying. The next level, n over 8. What about at level k? Do you see the pattern?
Yeah, n over 2 to the k plus 1.
Right, it would be n over 2 to the k plus 1. Because the exponent, if you use as powers of 2, 2 to the 1, 2 to the 2, 2 to the 3, the exponent's always 1 bigger than the level. So at any arbitrary level, it's going to be n over 2 to the k plus 1. And how many levels are there before we hit the base case? How many times can you split n in half before you get 1? Log base 2 of n. So this is the very bottom level. How much work is done at the bottom level?
None.
Well, it's not none. You got to,
Constant time.
yeah, some constant amount of work. So that's just here we've accounted for it, the amount of work by looking at each level separately. Sort of taking the recursion out of it. So how do we figure out the overall amount of work required by this method? Yeah, you just add them up. So the base case, it's 1. The recursive work is n over 2 plus n over 8, and so on, which is less than n. Basically, it's n times 1/2 plus 1/4 plus an 8 plus a 16 plus a 32nd. That gets closer and closer to 1, but never gets there. So it's less than n, so we can conclude that copying binary search is O of n. Yeah?
Would it not be viable to say that it is log of n? Or that it's log base 2 of n?
Well, that's not log of n. Why is copying binary search not log of n? Yeah? Because of copying. Remember? I did it for no good reason. except, I mean, it made my example work out. I'm playing a long game here. I've got 3 examples, and each illustrates something. Okay? Not too bad. Notice the top level all by itself is O of n. So that's what's unique. That's what's interesting about this case. I'm going to look at 2 other cases, but in this case, it was an algorithm structured so that the top level alone really dominates the algorithm. Okay, here's our recursive multiplication, where we're splitting in half. We're making 4 recursive calls, each with a number half as big, plus some linear setup work, and the base case is constant. So that's what we just talked about before we took a break. So let's do the same exercise here. What are you dealing with at level 0? What are you given to multiply?
Integer and length 2.
Right, 2 numbers of length n. So I'm going to do it that way. Yes, there are 2 numbers being multiplied, but we'll just focus on 1. Okay, and I guess I didn't have room to draw 2. Okay? Now, what happens at the next level? What are you given? What is E? Yeah?
You have 4 different bars, each of length n over 2.
Right, now you're dealing with 4 pairs of numbers of length n over 2. So think of these boxes representing pairs. So there we're given a pair of numbers of size n. At the next level of recursion, we're dealing with 4 pairs of numbers, each of size n over 2. The next level, it's 16 pairs, each of size n over 4. You see it's growing in a way that that last case didn't grow. So how much work are we doing at level 0? Sort of before and after the recursive call is made. Yeah, it depends on the number of, so we'll just say it's n, proportional to n. How much work are we doing at the second level? So if we did work proportional to n to deal with a pair of n-bit numbers, how much work will it require to deal with a pair of n or 2-bit numbers? Not counting the recursion. N over 2. But there's 4 of them, so the total amount of work across all the recursions at that level is 4 times n over 2. What's going to be at the next step? 16 times n over 4. What about at level k? Let's see, this is 4 squared times n over 4 to the first power. This is 4 to the first times n over 4 to a half. So you can see the pattern building up. So it's actually 4 to the k times n over 2 to the k. You work it out. And then we get to this base level here, log 2n.
Constant?
Each one is constant, but how many base cases are there? How many times do we reach the base case over the life of the entire algorithm?
4 to the k plus, or 4 to the k.
Well, if we plug log 2n into this, that would tell you how many base cases there are, right? Because this is the level, this is the lowest level. So if we plug that in for k, we'll get the number of base cases. So 4 to the log base 2 of n. I don't have the divided by 2 to the k. Why do I not have divided 2 to the k? Can't be a mistake.
Yeah, it should be. Because n over 2 to the k represents the amount of work being added to it, and because it's constant time, you're just multiplying the 4 to the log base 2 of n by 1.
When you do 2 to the power of log 2n, it becomes n, you cancel out the other.
Yeah, I mean 2 to the log base 2 of n would be n, but it still ought to be, oh, right. Okay, thank you. We plug log 2n in for k, we get 4 to the log base 2 of n. Okay, then there's an n right there. What happens when you plug log base 2 of n for k here? You get 2 to the log base 2 of n. They're inverses, so that's just n. So they divide and go away. So n is the same as 2 to the log base 2 of n, so we're just left with that. All right, so what's the total amount of work that's required? Well, let's add it all up. The base case work, there's a ton of base cases that happen, distributed through this recursive tree. Each one takes constant time, but there's a bunch of them. So I just multiply by 1, I get 4 log 2n, and that turns out, if you play around with it, to be n squared. So you get n squared recursive cases. Each at constant time, but you got to deal with them all. And then you got this sum here, which I factored out, just added everything else except the base case. I get n times this. The next to last level is log base 2 of n minus 1. What's that sum? What's the sum of the first k powers of 2? You tattooed on your brain. It's 1 less than the next power of 2. 1 less than the k plus 1 power of 2. So we can simplify that using that rule to this, which simplifies to that. So the amount of work we're doing just for the base cases is n squared. The amount of work we're doing everywhere else in the recursion tree is also n squared. So what's the overall complexity of the algorithm? It's n squared. But notice the base cases alone are n squared. So the previous case, it was just all that really mattered was the top level, the first layer. This example, the bottom level, is really all we had to account for. Yeah?
Does this kind of modeling also work for splitting things into like thirds and
Sure.
whatnot? We just change our
Yeah.
Okay.
Yeah, it works for splitting any way you want to split. The analysis might, then you're working instead of powers of 2, you're working powers of 3. So you have to use different formulas. But right, so that's another example of solving a recurrence. All right, here's one last example. This is just merge sort, just plain old merge sort. Split the array into 2 halves, recursively sort the halves, merge the 2 halves. What's the recurrence relation for merge sort? So remember, it's always in the form T of n is equal to something to do with the recursive cases plus the non-recursive part of the call. So the questions you have to answer is, how many recursive calls are made? 2. 1, 2. How big is the array in each recursive call? N over 2. And how much work is done here, exclusive of the cost of these 2 recursions? It's linear, because of the merge. So the recurrence then is 2Tn over 2 plus O of n. 2 recursive calls, each with size n over 2, plus a linear amount of work for the setup and the cleanup. Now, people always ask me, usually not during this lecture, but for the next 3 or 4 lectures, someone will ask, well, there are 2 recursive calls there, but each makes 2 recursive calls, and they each make 2 recursive calls. So there's really a ton of recursive calls. But what I want there is I just want you to look at the code and see how many calls were made. Just from this piece of code, 2 calls will be made. The cost of each of those is T of n over 2. So we're not trying to envision the recursion tree here. This is just a property of this method. Yeah?
So the cost in these cases come from copying half the array, correct?
Right. That's what merge will have to do a copy.
Mm-hmm. And the 2 recursive calls as well, copying half of them from low to mid minus 1 and then...
Well, the only place in this implementation, the copying is coming from... because copying is happening implicitly in merge.
So there's no cost to making that int left and int right? But that's what I'm saying. So the cost there is n divided by 2, like is written down.
Yeah, it's still linear, yeah.
Mm-hmm. But if you do have a case where you're going down recursively, I don't know if this actually exists, but if that didn't cost you making a new array left and right, would that be constant?
Sure. If we could merge in constant time, then this would be over 1.
Mm.
But forget about the copying part. You can't even do the merge in constant time because you have to iterate through both arrays. All right, so there's our recurrence. Now, let's think about this. You're sorting an array of size n. So at the next level, how many arrays are you sorting? How big are they? Okay, 2, half the size. The next level? 4, a quarter the size. So if we start talking about the work, how much work is done at the top level? Linear. Basically the cost of the merge. How much work is done at the next level? Okay, we're doing it twice, but the array is only half as long. So again, it's 2 times n over 2. The next level, we're doing 4 merges, each half as big. What about the kth level? Yeah, it's what? 2 to the k n divided by 2 to the k. Okay? We get down to the very bottom level, how much work is done? How much work is done for all of the recursive cases, all the base cases? So again, this is the lowest level, log 2n. If we plug log 2n here, what do we get?
2 to the log 2n.
2 to the log 2n, which is n. So it's n times n divided by n. Okay, so the base case work is linear. Recursive case work is n log n. Where'd that come from? How do we add up everything down to here and get n log n? Yeah?
It's n each time for log n times.
Right. Each level is n. Yeah. N, this is n, this is n, this is n. And there's log n in these levels. So it's just n times log n. So in this case, so overall it's n log n. Each level contributes equally to the complexity. Okay? So this is the general form of a recurrence relation. A times t to the n over b plus O of n over d. Plus O of n to the d. And again, where's the A come from? That's the number of recursive calls a method makes. Where's the B come from? That's the factor by which the problem size decreases each time. And this is just a bound that you put on the work that you do in addition to the recursion. It's going to be, it has to be O of n to some power. So that's the general form of recurrence relation. And I'm going to skip to the payoff here before I skip back to those 2 slides here. There's something called the master theorem. So what happens is, we just did 3 laborious analyses of divide and conquer algorithms. You know, figuring out how many levels there were and how much work at each level, how many times the base case was hit, and adding everything up. Kind of tedious. But people did this years ago, and they did it enough times, they saw a pattern developing when they did their solutions. And they found that there are different versions of the master theorem. This is the version from the book. They found that it fell into 3 cases. There's a case where d is greater than log base b of a. There's a case where d is equal to log base b of a, and a case where d is less than log base b of a. And I just showed you 3 cases. And the reason I picked those 3 cases to do is each one of them fits one of these cases. Okay? So let's look here. Copying binary search. There's our recurrence. So A is 1, B is 2, D is 1. Log base B of A is log base 2 of 1, which is 0. So which case are we in? D is 1, log base B of A is 0.
So it's our D and 2 D's.
D is greater than, 1 is greater than 0. D is greater than log base B of A. So we're in that first case, and so the bound we can put on that recurrence with the master theorem is O of n to the d. The d is 1, so it's O of n. So copying binary search is O of n. Okay? So if you can write down the recurrence relation, You don't have to go through that rigmarole we just went through to solve it. You just use the master theorem. Right? Let's look at merge sort. There's our recurrence. So A is 2, B is 2. What's D? 1 is the exponent of that n right there. Then you have to figure out log base B of A. Well, log base 2 of 2 is 1. Now, there is, in the past, I've allowed students to use calculators in the midterm. I'm not going to do it this time. Because there's nothing sadder than watching someone calculating the log base 2 of 2 on a calculator. You just need to know the log base 2 of 2 is 1. The log base 2 of 1 is 0. All right? And what if I ask you to compute the log base 7 of 2? I don't expect you to do that in your head, but I expect you to know that it's less than 3. Why is it easy to know that the log base 2 of 7 is less than 3? Right. You know, you're asking what's the power to which you raise 2 to get 7? Well, the power to which you raise 2 to get 8 is 3. So the power to which you raise 2 to get 7 must be a little bit less. Yeah?
Well, we have to make calculations in case big O of n turns into something like big O of n log n or big O of log of n. Or master theorem.
No. Basically, all we have are, we just have A, B, and D here. This thing here is always going to be power of n. So I won't make a problem that requires you to do a complicated calculation. All you're going to have to know is just the bare basics about logs. Okay, so the log base B of A is a log base 2 of 2, which is 1. Log base 2 of itself is 1. And so in this case, D and the log is the same. So which case are we in? Second case. So our answer is going to be O of n to the 1 log n, or O of n log n. That's what we got through the analysis. Okay, this was recursive multiplication. 4, recursive call, so A is 4, B is 2, B is the thing we divide by, D is 1, the exponent there is 1. Log base B of A, let's see, we're asking for the log base 2 of 4. What's the power to which you raise 2 to get 4? 2. Easy to do without a calculator. 2, the log is bigger than D, the exponent, and so we're in the third case. And our answer is O to the log base B of A. Well, the log base B of A was 2, we just figured that out. So it's O of n squared. Easy. I'll even, you can bring a cheat sheet to the exam. I'll even put this on in the midterm. So you don't even have to write this on your cheat sheet when you take the midterm. Yeah?
Will this master theorem be posted on Canvas?
Well, yeah, the slides are on Canvas, so here, and it's in the book. Okay? Yes?
So if you were to extend this and have like the bottom one with the 4 t, if you also had t over m divided by 4, you could just split them into 2 and solve for each part, right?
All right, so you're saying down here, if I change this to 4?
No, if you added to the complexity a t of m over 4.
Oh, I had t of n over 2 plus t of n over 4?
A different variable like m.
Yeah, well then, we wouldn't be able to use the master theorem. So
you can't split it into 2 parts and just use it on either part?
So the master theorem will only apply when you're dividing things equally. You're dividing into some number of pieces equally. So because you have to be able to describe the complexity with the recurrence of this form. So this bound has to be a polynomial bound. And this has to be, that's going to be an integer. These are typically going to be integers. Yeah?
The recursive multiplication one, d is less than log b of a, right?
Yep.
D is 1.
D is 1, that's less than log b of a, which is 2, so we're in the third case up there.
So then how come it looks like O of n squared fits into the top one?
It's because log of b.
Because log base b of a is 2. The log base b of a is 2. So you replace into the log base b of a with 2. It becomes n squared. Yeah?
So if we were to, instead of dividing each n-bit integer into 2. If we divide it into 4, would that make it into an n log base 4 n?
Okay, so if this recurrence were 4 times t of n over 4 plus O of n,
Yeah.
okay, let's figure out what that would be. A would be 4, B would be 4. What would be log base b of a? 1. So which case would we be in?
The second case.
It would be the second case because d would equal the log. And so it would be O of n to the, it would be O of n log n, yeah. Yeah. Yeah.
Will we ever run into cases where either D or log base B of A are equal to 0? Like,
Okay. Okay, so he asked, could D be 0? What would that correspond to? Constant, O of 1. O of 1 amounts to D being 0. O of n to the 0 is 1. So yes, D could be 0. Could this be 0? Yeah, that won't fly. You know, it has to be, in fact, there's the restrictions up there.
oh,
Right. B has to be greater than 1. You have to be making the problem smaller each time, and not infinitely larger. And it says A must be greater than 0. You got to be making some number of recursive calls for this to work. So the trick is to be able to apply the master theorem, you have to be able to look at the algorithm and write the recurrence. Once you write the recurrence, as long as it's in that form, it's just a mechanical job to pick out the answer. Now I mentioned that there are other versions of the master theorem, and I don't mean to say this one is wrong or anything. There are other versions that might have more discriminating cases that let you apply the theorem in to more examples. But this is a simple version that's easy enough to use and works most of the time. So we'll work with it. Next time what we'll start with is we will tweak our recursive multiplication algorithm to get one that is better than n squared. So we'll start with that next time.